Let's continue ZAERO Advanced Training, Section 7, Dynamic Response to Continuous Gust. So we'll review here the dynamic loads to continuous gust. The flight vehicles encounter air turbulence that contains flow eddies of various size and energy. And with the growing size of aircraft and the associated aeroelastic effects, the physical inadequacy of the discrete gust model became apparent. So in the early 60s, the continuous turbulence model using the power spectral density, or the PSD, techniques were developed. The PSD design load criteria have since then been included in the airworthiness requirements for transport aircrafts and the FAR-25 and JAR-25, in addition to the discrete gust criteria. And the continuous gust is defined in statistical terms by the root-mean-square value and the PSD function. So let's see how we do this in ZAERO. First, we'll look at the definition of the PSD and the root-mean-square. Now, since the PSD and the root-mean-square value of a stationary random function y of t will be used for the continuous gust analysis, we'll look at their definition used by ZAERO. So we have sigma yy, which is the RMS of y of t. Sigma yy squared is equal to the integral from minus infinity to positive infinity of the square of y of t. And now we let capital Y of I omega be the Fourier transform of y of t. Then the PSD of y of t is given by capital phi yy of omega is y of I omega times the conjugate of y of I omega. So the capital phi yy of omega is the PSD of y of t, and y star is the conjugate of y. Then the following equation here, 7.3, shows that the RMS of y of t can also be calculated from the PSD function. So if we start with our definition from equation 7.1 and then substitute in for y of t squared, we substitute in this double integral and then simplify. We come back to where phi yy squared is equal to 1 over pi of the integral from 0 to infinity of capital phi yy of omega. And then here's an example where we let y of t equal e to the minus t for t greater than 0, and it's equal to 0 for t less than 0. So if we do the time integration, we come up with sigma squared is equal to 1/2. If we go through the PSD and work through the equation, we also reach 1/2. So this is just showing that you can calculate the PSD either through integration of the time domain function or through the Fourier transform of the function. Next, let's review the mission analysis criteria. The mission analysis criteria is based on the use of the frequency of exceedance equation that is given in equation 7.4. So we have n of y, where n is the number of cycles per unit time in excess of the load, is equal to this equation. So we have our load y, np, that's our sum, is the number of segments in the mission being analyzed. So we are analyzing each individual segment and then adding them all up together. T of I is the fraction of time in segment I relative to the sum of all other segments. And then y1 minus g of I, this term here and here, is the load at the 1g trim condition. Now for lateral gust, this term would be 0. Now P1, P2, B1, and B2, those are our terms here, 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 and here, are constants depending on the altitude, and values recommended for the design are given in these figures below. This figure is for P1 and P2 as function of altitude, and then this figure is B1 and B2 values as functions of altitude. Continuing on, A bar YY is the root-mean-square incremental load of y to the RMS of the gust velocity, and it's expressed here in equation 7.5. So our phi yy of omega term in the numerator is the auto PSD of the load. Phi WG of omega is the gust PSD, and then omega is the frequency in radians per second. N naught is the characteristic frequency in hertz of the load Y, which is the average number of times per second that the load Y crosses the value 0 with positive slope, or equivalently as the radius of gyration of the PSD of load Y about 0 frequency, expressed here in equation 7.6. This figure here is an example of the frequency of exceedance of the bending moment at a wing section of a transport aircraft. Now if we take n of y wing to be 2 times 10 to the minus 5 cycles per hour, so that's right here, then the design load of y wing is 90 times 10 to the 6 inch-pounds. So we can see this curve here is the sum, so we drop down here, and this gives us our 90 times 10 to the 6. Next, we'll look at the design envelope criteria. The incremental load y design, according to the design envelope criteria, is given by y design is a bar yy times u delta, where u sigma is the design gust velocity given in this figure below. Now we have three different curves here, VD, VC, and VB. So in this figure, VB is the design speed for maximum gust intensity, VC is the design cruise speed, and VD is the design dive speed. If VB is selected, which is conservative, then mission analysis criteria is not necessary. If VC is selected, then the design load should be the higher load between design envelope criteria and mission analysis criteria, and VD provides the design envelope floor for use in conjunction with the mission analysis criteria. So here you can see we've got altitude on the vertical axis and design gust velocity on the horizontal axis. Next we'll look at the phased design loads. Now for design loads X design and Y design, for example wing root torsion and bending moment, the equation of the design ellipse is given here. So we have psi squared minus 2 rho xy times psi times sigma plus sigma squared is 1 minus rho xy squared. So this psi is x over u sigma times a bar xs, and sigma is y over u sigma times a bar yy. These are the normalized load coordinates. And the normalized ellipse is bounded by a rectangle that is tangent to the ellipse at the circled points. So this is our design ellipse in our normalized coordinates, and the circled points have sides psi plus and minus 1 and sigma plus and minus 1. So these are the four circles. Rho xy is the correlation coefficient given by equation 7.9, where phi xy of omega is the cross PSD of the loads x and y, and then sigma wg is the RMS of the gust velocity. Now for incremental loads about 1g flight, the ellipse is centered at the 1g load value. So this would be our 1g loads. Now, since every possible design load combination, for which there are an infinite number, given by the red curve, cannot be checked, the ellipse is circumscribed by a design octagon, given in black. Now the load combinations defined by the corner points A, B, C, D, E, F, G, and H are checked. And the line segments A, B, B, C, C, D, and so on are segments that are tangent to the ellipse. And the centers of CD here, EF here, GH right here, and AB right here are the intersections between the diagonal lines of the rectangle and the ellipse. And designing to this provides conservative design values. Next, we'll look at the power spectral density of the gust velocity. Now in ZAERO, we have two different PSD definitions. First is Dryden's PSD given by equation 7.10. So sigma WG is the RMS gust velocity, LG is the scale of turbulence. In civil aircraft gust loads determination, LG is taken to be equal to 2,500 feet for all altitudes, and this value was selected in FAA-ADS-53 and has been accepted generally. Next, we have von Karman's PSD given by equation 7.11, shown here. Now, both Dryden's PSD and von Karman's PSD have the following property where the if we take this integral, we obtain sigma WG squared. So in the textbook by Hoblet, the expression of Dryden's and von Karman's PSD functions have a pi in the denominator, and the RMS is defined by this equation. In the MSc Aeroelastic Analysis Manual, the expression of Dryden's and von Karman's PSD function have a factor of 2 in the numerator, and the RMS is defined by this equation. Now we note that because they're just using different conventions in their definition of the RMS. But as long as you use consistent conventions, in the end, you'll find that the PSD of the gust is just sigma WG squared. And so using our definitions of the PSD on the previous slide, we use these definitions of Dryden's and von Karman's PSD. And that will give you back sigma WG squared as the PSD, as it should be. Moving on, once either Dryden's or von Karman's gust PSD is selected in the continuous gust analysis, the cross PSD of two responses, x and y, can then be obtained by equation 7.13. Hx of I omega and Hy of I omega, shown here and here and here and here, are the frequency domain transfer functions of the responses x and y due to a unit gust, respectively. And this is a plot here of Dryden's PSD and von Karman's PSD. Next, we'll look at the frequency domain transfer function. So the frequency domain state vector due to a unit gust velocity can be calculated using equation 5.31, except we let WG equal 1. And that gives us equation 7.14. Now to recover the frequency domain transfer function of forces from the state vector solution, it's required to transform equation 5.40 into the frequency domain, which gives us equation 7.15. Now we have two methods available to compute the distribution of forces. The mode displacement method uses the left-hand side of equation 7.15. F of I omega is just kgh times c of I omega. And then the summation of forces method uses the right-hand side of equation 7.15. So that gives us equation 7.17 here. Now the sectional loads, L of I omega, such as the wing root shear, bending moment, and torque, as well as the control surface hinge moment, can be obtained by pre-multiplying a load integration matrix L to the distributed forces. So if L times F of I omega gives us the script L of I omega. And this script L may consist of the frequency domain transfer functions of N sectional loads. Substituting two of the transfer functions, Hi and Hj, into equation 7.13 from the previous slide yields the cross PSD of loads I and J. So we'll look at a numerical example of a generic transport aircraft. The state space model generated by ZAERO has been exported to MATLAB for control design. We use the wing ailerons used symmetrically for gust alleviation. It has a single input, which is the wingtip acceleration, and we're analyzing two control laws. A simple control law of a low pass and notch filters designed to alleviate deterministic gust response with a maximal symmetric aileron deflection of 20 degrees. And we have this resulting transfer function. And then secondly, we designed an H infinity 21 state controller designed to minimize the RMS response due to Dryden's gust spectrum with the RMS limit on control deflections. We then import these two controllers back into ZAERO and take a look at the wingtip RMS accelerations. So open loop, we have 58.24 meters per second squared RMS acceleration due to the gust excitation. With a simple controller, we can reduce that down to 49.36, and then with the H infinity controller, we can further reduce that to 31.4. So this is the type of analysis that you can do in ZAERO using the continuous gust module. So we'll look at the bulk data cards used for continuous gust. First, we have the CGUST card, which defines continuous gust parameters for the continuous gust loads analysis. SID is the unique identification number. Type is a character string that specifies the PSD function type. Type can either be Dryden or von Karman. So for type DRY, the exact representation of Dryden's gust spectrum is used. For VK2, the exact representation of von Karman's gust spectrum is used. And then if we append a P, DRYP or VK2P, then the PSD is also printed out on the output file. Additionally, type can be an integer. This integer is the identification number of a table D1 bulk data card that defines a tabular function of the PSD function in terms of PSD versus Hertz. However, this option cannot be selected if the state space continuous gust approach is used. It can only be used in the frequency domain gust approach. Next, we have LG, which is the scale of turbulence, and LG is not used if the type is an integer. The default of LG is 2500. So if your analysis units are in feet, then you can use the default. But if your analysis units are not feet, you would need to convert that 2500 feet to your proper units and put that value in here. So note the default is not 2500 feet. The default is just a value of 2500. So you want to make sure you're using the correct units. So I would recommend always just typing in the value for LG. Next we have V inverse field. This is 1 over the forward velocity, which allows ZAERO to convert the unit gust velocity to a gust-induced angle of attack. So you need to calculate what your velocity is for the given flight condition that you're doing your analysis, and then supply 1 over V in field 5. Next we have the X0 field, which is not used. Next is FMAX, which is the maximum frequency in Hertz for the frequency domain turbulence response analysis. And then next we have the DF field. The absolute value of DF is the frequency step size for the numerical Fourier transform computation. If DF is greater than 0, then the Fourier transform is computed using the slow Fourier numerical technique by direct numerical integration. If DF is less than 0, then the fast Fourier transform is used. And then lastly, we have GURMS, which is the root-mean-square value of the gust velocity. And GURMS is not used if the type is an integer, where you have user-specified gust PSD by the table D1 card. In the manual here, we have the Dryden and von Karman's gust spectrum printed out. The sigma WG is the GURMS, and then the LG field is LG, and then V inverse input is used as 1 over V in these equations. Let's look at remark 5 here, the reduced frequency corresponding to FMAX, which would be 2 pi times FMAX times ref C over 2V, where ref C is defined in the arrow Z card, should be less than the highest reduced frequency in the MK arrow Z card. Otherwise, a warning message is printed out. If Fmax is 0, then the highest reduced frequency in the MK arrow Z card will be converted to physical frequency and used for Fmax. Also, we should note remark 6, the computational time for continuous gust is proportional to Fmax over dF. Next, we have the CROSPSD bulk data card. ID cross is the identification number. Next, we have type. So type, much like the MLD print card, can be modal X, modal V, modal G, state X or state V, grid X, grid V, grid G, force for a grid point force, load mod for component load through the load mod definition, DMI or EXT out. And note that for the CROSPSD, both the X and the Y must be the same type. In other words, you cannot compute the CROSPSD from a grid displacement and then wing bending, for example. However, if you really want to do that, we have the EXT out option, so you can create a sensor to measure your grid displacement and then a sensor to measure your wing bending, and then use the EXT out card to export those two signals, and then use the EXT out option of the CROSPSD, but that's a little more involved. Usually, however, you're interested in the CROSPSD between loads, for example, wing shear and wing bending, in which case both of those would be the load mod option. Then next we have the two X and Y's. So grid 1 and C1 define the first component, and then grid 2 and C2 define the second component. So for modal X, modal V, modal G, grid is an index of the modes that represent the row position. And then additionally, C1 is not used. For state X and state V, it's the index of the state. And then for type equals grid X, grid V, grid G, or force, then grid is a finite element grid point identification number, and then we use C1 to define the component. So C1 can be 1, 2, 3, 4, 5, or 6. For type load mod, grid 1 is the identification number of the load mod card. For type DMI, grid 1 is the name of the matrix imported by either the DMI card or assigned matrix. And then for type EXT out, grid 1 is the identification number of the EXT out bulk data card. And the CROSPSD is referred to by the MLD print card for the output of the CROSPSD as a function of frequencies. Next, we'll look at some numerical examples for the continuous gust. So once again, we're going to be using the GBJ, the generic business jet model, and now instead of a discrete gust analysis, we're doing a continuous gust analysis. So the G-loads card refers to a CGUST card now. So the ID gust field of our G-loads card is 20, referring to the CGUST card with ID 20. Additionally, in our MLD print, we're referring to some CROSPSD cards, and then everything else remains the same as our previous discrete gust analysis. So next we'll look at the output file of ZAERO. The continuous gust analysis first computes the frequency domain aerodynamic forces due to gust excitation with a white noise spectrum and prints them in the output file for the first 10 modes. So this is the normalized real part of the gust QHG times white noise versus frequency for the first 10 modes. And this is the normalized imaginary part of the gust QHG times white noise versus frequency for the first 10 modes. Next, we'll look at our load mod cards. So we have 3 load mod cards to define the wing root shear, wing root bending, and wing root torque, which are shown here. The CROSPSD bulk data cards define the auto PSD. So this card refers to load mod 551 and 551, so that's the auto PSD for the wing root shear. This is the auto PSD for wing root bending, and then lastly we have the auto PSD for wing root torque. And then next we have 3 CROSPSD cards to define the CROSPSD between the wing root shear and wing root bending moment, the wing root bending moment and wing root torque, and wing root shear and wing root torque. And now we have 2 MLD print bulk data cards, both with ID 10, which are referred to by the G-loads bulk data card to output the auto PSD and CROSPSD defined by these 6 CROSPSD bulk data cards. Now in the first one, we have SOF equals no. So the PSDs will be computed using the mode displacement method, and our output file will be openmd.plt. Next, this MLD print card has the SOF field equal to yes, so the PSD will be computed using the summation of forces method, and then the results will be output to the file opensof.plt. Next, in the output file, the Gust spectrum is printed in the log scale. So this is the Gust spectrum. In the above printout, the input GURMS of 598.8, remember that's from our input file, is the input from the CGUST card, so that's right here. And then we look at the computed GURMS, which is 598.6, shown here. So the computed RMS value is computed by this equation. But remember, instead of infinity, this is actually from 0 to FMAX. So these two values ideally should be the same or very, very close to each other. If they're not equal, then that means your FMAX is not high enough. So the agreement between these two values indicates that the entry FMAX in the CGUST card is sufficiently high. So next we'll look at the output. So the PSD computed by the mode displacement method differs significantly in the results when we use 30 modes or 100 modes. As you can see here, this first peak is quite different for the auto PSDs and then the 3 cross PSDs. This indicates that even using 100 modes, the PSD results are not converged yet. Certainly at 30 modes, it's not converged yet. Thus, the mode displacement method is not the recommended method. It's used as a sanity check for the SOF results. So now we'll look at the SOF method. The PSD results by the SOF method are nearly identical between the 30 modes and 100 modes analysis, which indicates that the results computed by the SOF method are already converged using 30 modes. Next, the small peak of the PSD at a frequency of about 0.3 hertz, which you can see right here, and here, corresponds to the short period mode, and the larger peak frequency at 1.8 hertz, which is here, and here, corresponds to the first wing bending mode. So if we look here at the cross PSD of the wing root bending and torque, you can see these are negatively correlated. If we look at wing root shear and wing root bending, you can see that they're positively correlated. Next, we'll compare the mode displacement method using 100 modes and then the SOF method using 30 modes, and this confirms our suspicion that the mode displacement method is not converged even at 100 modes. So we would need even more modes to get an accurate answer for the mode displacement method. So this shows it's best just to use the SOF method. You can use much fewer modes. Next, we'll look at the N naught, A bar, and rho XY. These values are all printed out in the ZAERO output file, and you can use these values in the earlier equations we saw at the beginning of this section for your analysis. So our N naught value is printed out for our 3 auto PSDs and our 3 cross PSDs. Then we have our A bar, and then we have our rho XY, the correlation. And of course, for the auto PSDs, the correlation is 1. And then for the cross PSDs here. Interestingly here, we see that the correlation between wing root bending and torque are almost perfectly correlated with just an opposite sign. Next, we'll look at the convergence of N naught versus FMAX. So if we do numerical integration of N naught, requires a cutoff frequency FMAX specified in the CGUST card. So ideally, these integrals go from 0 to infinity, but of course in ZAERO, we can only go from 0 to Fmax. Now because the term omega squared in the numerator, this function must be sufficiently decayed at Fmax to achieve a converged integrated solution. And our sigma yy is Dryden's or von Karman's PSD. And then our hy, our Dryden or von Karman's PSD times hy is given by phi wg times hy squared. Once again, for Dryden's PSD, this is our equation. So if we look at what happens when we multiply by omega squared, that gives us an order of 1. For von Karman's PSD, once we multiply by omega squared, that gives us an order of omega to the 1/3. Thus, the convergence of N naught depends on the decay characteristics of hy of I omega squared at Fmax. Now, hy squared is usually a slow decay function, so this suggests that Fmax must be sufficiently large to ensure that omega squared times phi yy of omega at Fmax is small. So if we increase Fmax from 57.27 Hz to 68.73 Hz for the GBJ model, this shows that N naught for the 57.27 Hz Fmax is nearly converged. So if we compare for Dryden's PSD, wing root shear, this value is unchanged. Wing root bending, N naught slightly increases. Wing root torque, it is similar, and so on. And then if we look at von Karman's, we can see that the values are very similar. So this tells us that our Fmax value of 57 Hz is sufficient. Next, we'll look at a closed loop continuous gust analysis for the GBJ. So here we're going to add in a control system. So we are reading the sensor accelerometer that's feeding into our control system, which then feeds back to the symmetric aileron. And now if we plot the results and we look at the PSD of the 6 sectional loads of the closed loop system computed by the SOF option using 30 modes and the mode displacement option using 100 modes, once again this is illustrating that our mode displacement method is not converged, so you need to rely on the SOF option. And now if we compare the open and closed loop results, we'll look at the PSD of the acceleration at grid 325. It's significantly reduced by the gust load alleviation control system. So at these two low frequencies, this is our about 0.3 Hertz, and then our 1.8 Hertz. You can see the closed loop reduces that quite significantly. Out at about 5 Hertz, the response is similar, and then this peak at about 12.5 Hertz is also similar. If we compare N naught, A bar, and rho XY for our open and closed loop, you can see the results here. So A bar reduces the wing root shear, reduces wing bending, reduces wing torque. For the CROSPSD, A bar is similar for the shear and bending. It's reduced a little bit for the bending and torque, and then actually increases for the CROSPSD between wing root shear and torque. If we look at the correlation between the wing root shear and bending actually increases quite a bit, which kind of makes sense because with the closed loop you're actuating the aileron, so that increases your correlation coefficient between the shear and bending. Also between shear and torque, our correlation also increases.